Today we have a wonderful speaker. It's my pleasure to introduce Sebastian Will from Columbia University. Sebastian did his undergraduate at Mainz, and including a one-year undergraduate thesis research at MIT with Wolfgang Ketterle. And then he got his PhD also from Mainz, working with Emanuel Bloch. After which he spent a number of years at MIT with Martin Zurlein, first as a postdoctoral fellow and then as a research scientist, before joining Columbia as assistant professor in physics. Sebastian, in his short career, has already won an impressive number of awards, including an NSF Career Award and a Sloan Fellowship. We're delighted that you're here. Sebastian is going to tell us about synthetic dipolar quantum matter. Sebastian.
Yeah. Thanks so much, Shiwei, for the invitation and for the kind introduction. And it's a pleasure to be here and an honor to open the Quantum Cafe season, as I understand it, for this fall. So, yeah, in the talk today, I'm going to tell you about synthetic dipolar quantum matter. So it's basically what I'm going to talk about is in some ways a new kind of quantum matter. I will try to tell you how we synthesize it and what we can do with it. And in the first few slides, I already give away the main message. So we make Bose-Einstein condensates of sodium and cesium, overlap them, and make molecules out of them, pairing up atoms of sodium and cesium and make molecules out of them. This gives us gases of dipolar molecules. We have pushed this forward over the last 2 years or so, really the molecule making and understanding. And I'm going to tell you, this is the big picture, and I'm going to tell you the details that get us there and what the potential of this new system is. I really want to start out by thanking my group. Basically, in the 2 years since 2.5 years now of the COVID dilemma, they really have pushed forward in a way that I couldn't have imagined. That was very impressive what they were able to accomplish in a very short time. And I will introduce the key people at the end of the talk. Yeah, so to give some context, I want to kind of sort molecules into categories that you may have heard before. It's not a good place to stand.
It's okay.
So basically, you've heard about trapped ions. It's a very widely used quantum system based on charged atoms. Typical ionic quantum system have 1 to 1,000 ions or so. They have long-range interactions that come from the Coulomb-Coulomb interaction between the ions, and you can form, interesting ordered states like Coulomb crystals in the system. On the other hand, and that's sort of the background where I come from, they are ultra-cold atoms. Ultra-cold atoms are neutral particles. Typical system sizes that are realized are between 1 and 100,000 atoms. The interactions typically between ultra-cold atoms are contact interactions. So they are very short range. Ultra-cold atoms we can trap with optical means, with lasers. That's in contrast to ion traps that are trapped in RF traps. And we can confine ultra-cold atoms in artificial crystals made out of laser light, also known as optical lattices. So in some way, ultra-cold dipolar molecules that I'm going to talk about today fall in between these two. Ultra-cold dipolar molecules are neutral particles. The system sizes we create range from 1 to 10,000s of molecules. So kind of similar to what can be done with atoms. Then there are long-range dipole-dipole interactions between the molecules, and it turns out they are controllable, and I'm going to show that. Nevertheless, we can use optical trapping techniques that have been perfected for ultra-cold atoms. And it is expected that ultra-cold dipolar molecules can be used to create interesting, strongly interacting phases, for example, like dipolar crystals. So let's quickly review what I mean when I talk about dipolar interactions. Usually in our systems, we care about dipoles that are aligned, so they're not pointing in any random direction, but they're parallel to each other. Then in this case, the interactions can be given like shown here. It's proportional to the dipole moment squared and inversely proportional to the distance between the dipole cubed, so 1/r cubed. Then there is an anisotropy that is encoded here, it's angle dependence, and the limiting cases are that when the dipoles meet side by side, they repel each other when they meet head to tail, they attract each other. And that can give rise to all kinds of interesting effects that can be exploited in many body systems. So that's sort of the general dipolar story. And contrasting this with the contact interactions that are prevalent in ultra-cold atoms. For ultra-cold atoms, we have a contact interaction here expressed like in the form of a delta function potential and with a prefactor A, the scattering length that characterizes the strengths. But in order to interact, or as a result of this delta function type interaction, basically you need to have wave function overlap between the atoms for them to actually overlap. When you have dipolar interactions, things are a bit different, so that you actually get interaction at a distance. You don't need wave function overlap. And this is an ideal system, or potentially ideal, to create interesting, strongly interacting phases, and in particular using the long-range interactions to actually create highly entangled many-body quantum states. So this has been recognized before and has been applied in other quantum systems that can be created with techniques that are also borrowed from the early days, from the ultra-cold atom community. So it's resting on this. One research direction that has been really intensely pursued over the last 10 years or so is magnetic atoms. Chromium, erbium, and dysprosium happen to have unpaired electrons, unpaired spins, and therefore a large magnetic dipole. When it comes to magnetic dipoles, it's large, but in terms of, if you express it in terms of dBi units, it's less than 0.1 dBi. These interactions are not tunable. You just have the magnetic dipole moment that your atom gives you. And to see actually interesting, strongly interacting phenomena, you need to drive the density in the system fairly high. But nevertheless, the systems are long-lived, and you can study itinerant phases. So what, one of the hallmark results of the last few years is the observation of droplet phases in these systems and the observation of super solid phase, a peculiar type of super solid phase. So that is sort of one direction that has so far been pursued. The other one is Rydberg atoms. Rydberg atoms are also atoms, often alkali atoms, that are excited to a very large principal quantum number orbital. They are highly polarizable, which gives rise to electric dipole-dipole interactions. In terms of dipole moment, we look at dipole moments of 1000 dBi or so. The interactions are tunable within certain limits, but they're always extremely strong. The densities can be fairly low in these systems to interact, to observe strongly interacting physics. But one downside is that the systems are short-lived because the Rydberg excitation is very short-lived. So 100 microseconds or so is a typical lifetime, which means you cannot study itinerant systems. Basically, if you start exciting into a Rydberg state, you have a frozen system. So you will not be able to study something where the atoms need to move to kind of equilibrate in a new ground state or so. So these are basically sort of the limiting cases that have been studied. Right now, again, molecules fall somewhere in between. The molecules that we create are made out of two alkali atoms typically. They are electric dipoles. Dipole moments are between 0.5 and 5 dBi. That brings with it that the interaction energy is tunable around the energy scale of the kinetic energy in the system. So it's really, you can reach regimes where, kinetic energy and interaction energy are almost equal, and that's where stuff gets interesting.
Do cesium and sodium, presumably they form a molecule?
Yes.
Right? And what is the dipole moment of that?
Yeah, we are getting to that. I'm going to put it in context of what has
I
been.
want to understand.
But it's about 5 dBi in our case.
It's
So
5 dBi?
Yes. Yeah, it's one of the strongest dipole moments you can achieve by alkali atoms.
So Sebastian, so I'm a little more familiar with the Rydberg
Yes.
atom setting. Do I understand correctly that one of the advantages of the dipolar molecule setup is that the lifetime? What would you highlight as being the key?
So I think so the lifetime is something we need to discuss. I put a question mark there,
Yeah, I see
and
that.
that is what has actually been an important question in the field for a long time, and I will show you new data that will be very helpful in this respect. I think the strongest point about dipolar molecules is that you really have the interactions are not exceedingly strong. Like in Rydberg cases, basically you lock down the atoms in place, and you can use Rydberg interactions to study crystallization or effective spin dynamics, but you will not be able to create phases where you actually need moving particles. Any superfluid, any
Itinerant phase.
any itinerant phase you cannot study with Rydberg atoms, because the lifetime is too short, because at these ultra cold temperatures, basically the kinetic energies are such that movements are always happening on the time scale of milliseconds.
The technology is different too, right? In the Rydberg case, the atoms are trapped by tweezers.
Yeah,
Here, you're going to use lattices, but I don't want to
yeah,
anticipate on
we're going to get to that. Basically, we
use
can use
optical.
both. In Rydberg, over the last few years, tweezers have become very popular because basically you don't need the atoms to be close. You can have them far because the interaction is so abnormally strong. So that's why tweezers are popular here. Lattices, here you actually see an example of Rydberg physics in a lattice from the group of Emanuel Bloch, where actually also in a lattice you can study Rydberg atoms, but more popular in tweezers. For molecules, we can do both, and we will do both. I will show you.
If I remember right, if the bi is two charges separated by a Bohr radius. That's definition of 1 dBi. Right?
Actually, there is a factor of 2.7 between that, but yeah, an electron charge separated by a Bohr radius is 1/2.7 dBi.
I see.
Yeah.
Just a couple of basic physics questions. So when you say that dipole interactions are tunable, I know how to increase a dipole moment, but
I will get to that.
it's both ways tunable. You can decrease a dipole.
You can go from 0 to a finite value.
Okay, but you cannot take a too large of an interaction and reduce it. There's no trick that.
Yeah, for Rydberg atoms, the way to reduce it is you would go to a Rydberg state that has a lower principal quantum number, but the issue is the lifetime goes down.
But there's no like dynamic tricks where you can kind of like just put it into some dynamically sort of evolving state.
Time averaging or something. You gain some fact, you can do that, but again, not a fact, you don't reduce by orders of magnitude.
Right.
You reduce by 1/√3 or 1/6.
And the other basic question, when is there a simple sort of a decay channel? What dominates the lifetime? What's the biggest?
Of which system?
All three. I mean, each one. I'm just curious.
Yeah. So all these systems are non-equilibrium systems in the sense that the equilibrium phase of ultra-cold atoms is not a gas phase at a density of 10 to the 13 per cubic centimeter, but it's a solid. So basically you're fighting always against 3 body losses, but in ultra-cold atoms they are on a time scale of many seconds, tens of seconds often, so it doesn't really matter. It turns out actually chromium is not a popular atom anymore because the 3 body loss is actually very fast compared to erbium and dysprosium. With Rydberg systems, basically you can trap in tweezers Rydberg atoms for many seconds, But what limits you to study interesting physics is the lifetime of the Rydberg state. So as soon as you decay from the Rydberg state, your interaction is gone, and
Which is done by emitting light.
yeah, it's a spontaneous emission. Yeah,
Yeah.
sorry, yeah. Mhm. And in the case of molecules, we're going to get to that. Yeah. Okay, so basically the potential of molecules has been understood like for the last 20 years. There have been proposals over the last 2 decades, basically what you could do if you are able to make a strongly interacting ultra-cold gas of dipolar molecules. So, proposals of novel many-body quantum systems, the bilayer system. You could use the dipole-dipole interactions of the molecules in a lattice to study spin physics in new ways. There is a whole range, it's a huge subclass of proposals of using molecules for quantum information because you have highly coherent internal states in molecules. And also you can study quantum chemistry. But basically the challenge has been creating a stable, usable dipolar molecular gas. So the appeal of the molecules, as I just kind of alluded to already, is the internal states. They make it interesting, but also hard. So here I'm plotting for a molecule energy versus internuclear distance. So it's only referring to dipolar molecules here. We have here like a Born-Oppenheimer type potential. And in this potential live vibrational states. And then, so typical spacings there are on the terahertz scale, corresponding to energy, to temperature equivalents of like 100 Kelvin or so. Then on top of that, not shown, you have rotational states, typically spaced by energies of 10 gigahertz or so, corresponding to temperature scales of a Kelvin or so. And then there is on top of that even a hyperfine structure where the energy splittings are even smaller, like 100 kilohertz or so. So basically, that if we want to control molecules as well as we can control ultra-cold atoms, we need to be able to prepare molecules in perfectly defined quantum states. And that is only possible when we are able to cool them to the microkelvin temperature. So that's challenge number 1. The other challenge is that we want to specifically prepare the molecules in the absolute low vibrational ground state, because that's where the dipole moment is large. It has been done for many years to prepare molecules in the highest vibrational state. These are Feshbach molecules, but they have no dipole. So we want to go here. That's a challenge. Okay, so the question is, can we reach this ultimate level of control for molecules? And it turns out we can, not by directly cooling molecules, let's say with laser cooling and the other techniques that we know from atoms, but rather by putting molecules together by atom by atom assembly from overlapping mixtures of ultra-cold gases. So a key technique here is still, and the first step to making the molecules is using a Feshbach resonance. So I guess most of you have heard about Feshbach resonances in ultra-cold atoms. It's our way to usually our way to control the contact interactions between atoms. So as a function of magnetic field, a resonance arises where I can tune the scattering length from positive divergence to negative divergence. So it gives me a powerful knob to control contact interactions. But actually, the very reason that gives rise to the scattering resonance is the presence of a molecular bound state that is coming as a function of magnetic field into resonance with free atoms. And I can now reverse the situation. I can start with my molecule gas above the resonance and slowly ramp the magnetic field across the resonance and adiabatically convert atom pairs into molecules. But these are extremely weakly bound molecules. So what I told you so far is I take a pair of atoms, control the interactions via a magnetic field, and then I create a weakly bound molecule. Now, this weakly bound Feshbach molecule has no dipole moment, as I said before. So what do we need to do next? Well, we need to bring it to the low vibrational ground state. Basically, we shrink the molecular wave function to something significantly smaller. And to do that, we need to take out internal energy that is equivalent to roughly 7,000 Kelvin. And we want to do it in a way that we are not heating the molecular ensemble that we created from nanokelvin or 100 nanokelvin cold gases of ultra-cold atoms. So that's an experimental challenge. I'm not going to talk too much about it, but show you a bit more later. So that gives us our ground state molecule, and this shrinking we do with a 2-photon process that is called stirrer. So when we do this successfully, we are creating a 3-dimensional cloud of molecules, typically at temperatures of 100 nanokelvin or hundreds of nanokelvin. So actually, by the end of the talk, I will have to slash a 0 in that. We're getting much colder now. The typical extent of these gases is like tens of micrometers. Typical dipole moments between 0.5 and 5 dpi. And these are pictures that we usually take. So this is an absorption image of a cold cloud of molecules. In this case, it's an NaK molecule cloud that I made in my postdoc time at MIT. But the history basically of making these molecules is not very short, actually. So the first molecules in this way have been created in 2008 by Debbie Jin and Jun Ye. So it's not a new technique. But actually, it turned out shortly after the first molecules were made is that the losses in these molecular gases are actually fairly strong. You basically are in a situation that when 2 molecules meet, they undergo rapid loss. What the origin is was not entirely clear for a long time. Initially, the understanding was that you make a chemical reaction where, in this case, KRB plus KRB turns into K2 plus RB2. It's an interesting quantum chemistry thing, but it limited the lifetime of the molecular gas. Then there have been other systems that have been studied. So, for example, despite the short lifetime, it was possible to load the molecules into optical lattices. However, with a very low filling fraction of below 10%, and then dipole-dipole interactions were studied that could be interpreted as spin exchange in the lattice. So it's interesting, but not in a particularly appealing regime because the lattice filling was so low. And the reason was you couldn't get the cloud cold because there were exceeding losses. Also, I did some work with these, kind of lossy molecular gases. For example, we were able to show nuclear spin coherence time on molecular gases on the 2nd scale, which is fairly long and has potential for quantum information applications, but still, the whole system was battered by the fact that it was not very long. In the meantime, since over the last 15 years, there have been a couple of groups, like a dozen groups worldwide, that have created molecules, KRP, RBCS, NaK, NRP, NaLi, and NaCs. The latest edition is here at Columbia. But again, basically short ensemble lifetimes have actually limited the progress in this field. This has changed with progress in the last year, basically. The Gila group, Jun-Ye, has been able to show for fermionic KRB that you can use a so-called resonance shielding method to increase the lifetime in the gases. And also with the fermionic molecule, NaK, Immanuel Bloch's group has shown that you can use a technique that's called microwave shielding to increase the lifetime of the gas. But this was both in fermionic systems. In fermionic systems, you have a p-wave barrier and losses are much suppressed intrinsically. And one should say both groups have worked for more than 10 years on these systems to get to that point. Important question that we tried to ask there is, what about molecules? What about bosonic molecules? Bosonic molecules, you have no p-wave barrier, things should be much harder. And that gets us now really to the meat of the talk. We're gonna introduce to you what we are doing. So first question is, why do we choose NaCs molecules? So NaCs molecules are bosonic molecules. We find that interesting because the majority of existing experiments work with fermionic molecules, and with bosons, there's a potential to actually create a BEC of molecules, which is going to be, if it works, a very interesting dipolar quantum fluid. Then NaCs, as I briefly mentioned earlier, is the bialkali molecule with the largest dipole moment that you can make. And compared to KRB that was done at Gila by Julie at the Beijing, or that is being investigated, that's just a factor of 10 difference. But what matters is basically dipolar interaction energy, which goes quadratic in the dipole moment. So we are looking at interaction energies that can be up to 100 times larger in the system, which is going to make it qualitative. And we can tune the interactions. So that's addressing the question that came up before. Basically, by exposing the molecular gas to an external electric field, we are determining how well the dipole is aligned in the lab frame. By exposing the molecules to larger field, we can align them more strongly and the interaction becomes stronger. And that is a powerful tuning knob, and turns out also NaCs is very good in this respect because you can reach large induced dipole moments at fairly accessible electric fields in the lab. So it's a challenge in the lab to actually integrate into like a whole atom and molecule cooling apparatus additional electric fields. So if you don't need to apply too high electric fields, you're going to be very happy. Interesting systems to study now, particularly with NaCs. We were initially thinking when we started this like 4 years ago of 2D systems. Basically thinking of a plane in which we arrange the molecules and we just align the dipole moment perpendicular to the plane and look at repulsive interactions. We basically have a competition between kinetic energy and interaction energy in the system. And since we have the molecules in 2D and have dipolar repulsion between neighbors, we should get actually a suppression of fast losses in the system. So that was actually one of the initial motivations to go to NaCs and have with particular 2D systems in mind. So it's a system where you can study interesting physics and at the same time suppress loss processes due to repulsive side-by-side interactions. So for this particular system, this has been studied theoretically for a while, actually. There have been phase diagrams proposed. So basically, you see a phase diagram here with temperature on this axis and interaction strengths on this axis. This RD parameter is essentially the ratio of interaction energy to kinetic energy. And you see for fairly weak interactions, you expect a superfluid, dipolar superfluid, which can be quite strongly interacting also at some point. If you crank up the interactions further, you should be able to transfer into a crystalline phase. And that's a self-organized crystal. I really want to contrast that with, optical lattice systems where you impose a laser setup or laser potentials on atoms, which is completely rigid. Here in this case, it will be a self-organized crystal phase with 4 known modes where you can study defects, all these kind of things. So an interesting problem there is actually the melting of the crystal in 2D. It's, as far as I understand, a long-standing question, what really happens, and that would be really interesting to study in a way that we can actually really image the crystal and study how it actually melts.
So there's an overall confining potential?
Yeah, there's an overall confinement potential. We can choose if it's harmonic or if it's a box potential.
Yeah, you can engineer that, right?
Mm-hmm.
Kind of flat trans.
So there we can really borrow from techniques that have been optimized for ultraflow atoms. Basically, everything that works there works for molecules, for these types of molecules too. So studying this phase diagram, was a motivation for us, enough motivation for us to go into this adventure of creating these molecules. And the key thing to look at now is there have been made molecules before. I showed you the list. And if you go through realistic numbers, you will find that with none of the molecules that have been created so far, you will get strongly interacting enough to reach the crystal phase.
Can I just ask something? So if I allow myself to just imagine that you have a bucket flat confining potential,
yes,
shouldn't you be able to tune across this phase diagram by basically taking the same dipoles and squeezing them tighter? What limits?
Yeah. So this is on principle possible. It's very effective because of 1 over R cubed.
Right.
But you want to not go to too high density for 2 reasons. One is when the density becomes high, you get inevitable losses. Again, we're going to address the loss question later in more detail. and maybe we have found a solution for that. But then the other thing is you also want to be able to image each and every molecule with single site resolved imaging. And basically that's an optical method that limits you to resolutions of like a micrometer.
There's an optimal density.
There's an optimal density. So ideally you want to have a density where the interparticle spacing is about a micrometer, because then you can see each molecule. Yeah.
I have also a question to the formation of the molecules.
Yeah.
So what I didn't get is the following. Normally, molecules are formed via three-body scatterings, and you will probably need that here as well, because otherwise they will not be formed. And then this is a lost channel because the molecule is not trapped anymore. So what is different here? You have the three-body collisions, and the molecule is formed.
There's no three-body.
Why not?
In the Feshbach resonance, you go adiabatically from two free atoms without any need for energy dissipation. Adiabatically, you follow an eigenstate that transforms your pair of atoms into a molecular bound state. That's the magic of the Feshbach resonance.
But I thought always this breaks energy momentum conservation.
No, basically you make use of the fact that you have a degree of freedom with the Zeeman energy in the system. That's what you tune with the magnetic field, and that takes away your energy.
Yeah. Okay.
We are talking about molecules that have a binding energy of a few tens of kilohertz. This corresponds at an excitation temperature of a microkelvin. You will break this Feshbach molecule. It's not a stable molecule. That's why we need to do more. That's why we have this shrinking of the molecules.
And why is the molecule still bounded by your optical fields?
Say again?
Why is your molecule still bounded by your optical fields when the atoms were? Why is the molecule still in a trap?
The Feshbach molecule is basically two atoms on a stick that are far apart. You can treat them just like two atoms when it's a Feshbach molecule. The question is much more interesting is the ground state molecule and the low vibration ground state, is that optically trapped?
Yeah.
That's actually a question that is not so easy to answer a priori, and we found experimentally that it's trappable in the same kinds of lasers.
Thank you.
Yeah.
Why does sodium cesium have such a large dipole moment?
So the chemist's answer is the electronegativity between sodium and cesium is very different. You get a deformation of the electron shell. That's significant. Basically, you have a light atom, a heavy atom, then you get a larger deformation.
Lithium and
lithium cesium you can do, and actually the dipole moment is ever so slightly larger, but lithium cesium is one of the few chemically reactive bialkaline molecules. I didn't go into details of that discussion because that would open up a whole different field. So lithium cesium has been tried to be made by Cheng Chin in Chicago, and it has been a very long endeavor that hasn't been fulfilled yet.
So I actually promised Sebastian that we would do the more elaborate questions at the end. So maybe we should do a little bit of.
Yeah, it's okay. Yeah, it's okay. I'll adjust the number of slides by. It's a very good questions. I think it helps a lot to clarify these points. So, good. So in the case of NaCs, we can reach ratios of dipolar interactions to kinetic energy of 50. So we are really covering this phase diagram, and that's what we find very exciting. But doing NaCs molecules was a pretty crazy endeavor because nobody had ever cooled sodium and cesium mixtures before. And anybody who has studied just one atomic species and cool them to ultra cold temperatures knows already how much work that is. And to do two at the same time and not knowing what's happened, how you cool them together, how you can cool them together was a bit of a crazy thing to do. It was the last bialkaline mixture to be explored, so not much was known. Cesium itself is a kind of unpopular atom because it has very difficult scattering properties by itself. I will not bore you with all the details, but cesium was the last alkali atom to be Bose-Einstein condensed, and it has cost several faculty their tenure. Attempted to so. And then, as I said, NaCs is a bosonic molecule, which we find interesting, but it comes at the cost of absence of a p-wave barrier. So we expect even stronger losses in sodium cesium. Okay, so what did we do? First step is creating overlapping condensates of sodium and cesium, creating sodium cesium mixtures. This is something we have embarked on. So basically, just to give you sort of the quick experimentalist view what happened, we moved into empty labs roughly 4 years ago. So they looked like that. Then we spent the first year to build the system that allows us to make Bose-Einstein condensates of sodium. In parallel, we started to attach to the system the things that are necessary to do laser cooling of cesium. Then COVID hit, and for 3 months nobody entered the lab. Then, just a month or two after coming back from the lockdown, I mean, the team really worked like crazy and got a cesium BEC in conjunction with a sodium BEC. And then things sped up even more. We built the laser system that is needed to shrink the molecules from the Feschbar state to the absolute ground state, detected the absolute ground state, and roughly a year ago, we made the first ground state molecules of sodium cesium. So within 3 years, we did this. So the context is, typical time scales more like 6 to 10 years. So I'm very proud of my team. So yeah, that's the empty lab. That's how it looks today. That's the laser system for laser cooling of cesium. That's the laser system for laser cooling of sodium. That's actually the heart of the experiment. That's a vacuum chamber in which all the cooling and trapping and molecule formation happens. So in this chamber, it might be the emptiest place in New York City. It's like the pressure of less than 10 to the minus 12 torr. So that's where stuff happens. You can zoom into this viewport here and look at a laser-cooled cloud of sodium. So that's like a few billion sodium atoms at 200 microkelvin or so. And with that kind of laser-cooled cloud of sodium atoms, we do the next step to create BEC. We trap it in a magnetic trap and followed by trapping in optical trap and evaporatively cool the system to BEC. So this gives us BECs, very healthy BECs with several millions of atoms at temperatures of 100 nanokelvin or so. And the funny side note is that that's probably the coldest place in New York City. Unless somebody else has a BEC machine that I don't know of. So here you see the formation of dual BECs of sodium and cesium. So we cool down further from left to right. These are thermal clouds, and you see first we hit a sodium BEC as we continue cooling, and at the very end we have overlapping BECs of sodium and cesium. So these dark intense spots are the BECs. We find practically that these overlapping gases of sodium cesium are actually very long-lived together, which is something very unusual in alkaline mixtures, and it's interesting in itself. So when we make two overlapping BECs, it's two overlapping superfluids. You can actually study interesting physics with that too. We kind of left it on the side so far, but basically, there is a lot of theoretical work on, transfer of vorticity between different superfluids and all these kind of things related to neutron stars and all this, Anyway, we didn't look into any of this. Basically, what we cared about is these are ideal conditions for the creation of ultra-cold sodium cesium molecules. We're going to go to that. Next step is creation of Feschbar molecules. Turns out the magnetic field at which we can create these molecules was predicted to be fairly high at 840 Gauss. It requires a pretty complicated contraption in the experiment. You need to run 400 amps of current through a coil, and you kind of need to control the magnetic field to a pretty high degree of stability. But anyways, we put that in and found actually the Feschbar resonance that was predicted at 40 at 864 Gauss. With that Feschbar resonance, and I spare you the details, we were able to ramp across it adiabatically and create then gases of sodium cesium Feschbar molecules with up to 40,000 molecules. So, just as that is a high number for systems that create H1 molecules in this fashion. And that's very good because it allows us, to create many dipolar ground state molecules, which allows us to get to fairly high densities and all that. So that's the context. We also studied the phase-space density of these very loosely bound molecules. And since the number is so high in our system, we actually are in a situation that already here we have a peak phase-space density of almost 0.1. So that's just a factor of 10 in phase-space density away from a BC of molecules. But here I'm not talking about ground state molecules yet. This is still Feshbach molecules. That's a near degenerate gas or bosonic molecules that have not been done before. So that's very good conditions. What also matters for us is how long do these Feshbach molecules live, because we need some time to do this process of shrinking the absolute ground state. So we looked at the lifetime of this Feshbach molecular gas, and there we find the lifetime is like 5 milliseconds. That's very short, but it turns out the stirrer process that we use for shrinking the molecule only takes 50 microseconds or so. So we are good on that front. Good enough to make molecules. Okay, now let's approach the absolute ground state. So for that, we need to understand the molecular physics a bit more. So initially, so here you see the real von Oppenheimer potential for NaCs, energy versus interatomic distance. Initially, we make Feshbach molecules. We want to go to the absolute ground state. Turns out the Feshbach molecule has dominantly triplet spin symmetry and the absolute ground state singlet spin symmetry. So you cannot do a direct coupling, optical coupling between the two, spin for bin. So we go via a 2-photon process where we use an electronically excited state as a bridge to go to the ground state. And this is what we want to implement as a fully coherent process. So that means we need lasers that are phase coherent with respect to each other. And that's not trivial for lasers that have a completely different color. So that's a technical problem we need to solve. A practical problem we need to solve is that we first need to find the electronically excited state of NaCs that actually serves as an adequate bridge and couples both strongly to the Feshbach state and the absolute ground state. So for this, we did the most precise spectroscopy that has ever been done on NaCs and identified an electronic state that would provide this coupling. The phase coherent laser system we built by locking 2 lasers to the same ultra high finesse optical cavity. So that's a piece of glass with 2 mirrors on each side that serves as a passive frequency reference and allows us to stabilize the lasers that operate at hundreds of terahertz of frequency to like 100 hertz stability. So this is basically techniques that are used in atomic clocks otherwise. So anyhow, with this in place, we were able then by doing EIT type dark resonance spectroscopy, we were able to locate the absolute ground state due to the presence of the EIT peak in the sort of coupled 3-level system. And that brought us then in a position that we could do the stirrup transfer. So basically what's happening here is that we are starting with a cloud of Feshbach molecules, and then we shine in the 2 lasers here simultaneously, but first in a way that the orange laser is strong and the red laser is weak, and then we kind of adiabatically change the intensity of the lasers. And what that does is that a dark state of the coupled 3-level system adiabatically gets transformed from the Feshbach state into the ground state. So it's a fully coherent process between states that are separated in energy that corresponds to 7,000 Kelvin of temperature. It's a quite mind-boggling thing to think of, and it's reversible. So we first go into the ground state, stay there, and then we come back. Then we recover. Initially, we see the Feshbach molecules vanish, and then we recover them again. This was actually early data where we generated 20,000 molecules with an efficiency of 55%. Ideally, we want single molecule resolution, so we want higher efficiency. So over the last few weeks, we actually were able to drive this up to 85%, and perhaps there's even some higher there. So these are some of the best efficiencies that have ever been achieved in dipolar molecule research, which is going to be very important for the reliable study of many
You get these numbers by looking at the optical transitions.
Yeah, we basically
molecule versus we call the.
Yeah, so basically what we compare is, how many Feshbach molecules can be recovered when we make a round trip through the ground state. And then we compare the two numbers and we see then the efficiency of a single stirring process from that.
Just the question, my question was, how do you count? How do you know it's 40,000?
Oh, I see. So basically we need to calibrate. This is the absorption image of the molecules, and we need to calibrate. We basically need to determine the scattering cross section for optical scattering, and from the optical density, this is a shadow cast essentially on a laser, and from the intensity of this shadow cast we extract the density of the molecules, and from that the number of the molecules. So here we don't use single site imaging yet. We are actually currently in the process of doing that. So the next thing that we did is we want to see what kind of dipole moments we can achieve. And there we need to dive a little bit deeper into the internal structure of the molecule. So we prepare the molecule with the stirrup process in the rotational ground state. But there are higher rotational states, basically a ladder, and that is given by the rotational constant by the rotational spin, by the rotational spin squared. And then we want to apply an electric field. And what the electric field does, it mixes opposite parity states, which leads to alignment of the molecules in the lab. So basically, we can calculate that a priori from sort of numbers for the rotational constant and dipole moment that have been determined predicted before. You see here this tuning curve that I showed before. And we can do this now in the experiment. So we integrate into the vacuum chamber, a set of transparent capacitor plates that are arranged around the molecules that allow us to expose the molecules to electric fields of several kilovolts per centimeter. And then we monitor the start shift of the molecular ground state, which is directly related to the dipole moment. What we find is that with this, in our setup, we can reach a dipole moment of induced dipole moment of 2.6 dBi. And that's also unsurprisingly because of the large intrinsic dipole moment. Sodium cesium is the highest dipole moment that has been ever achieved in dipolar molecules. Now let's put that on the map on the phase diagram that I showed before, right? So basically, what we care about, can we go to this crystal phase? So where are we now with this 2.6 dBi? We have a characteristic range at this point of the dipolar interactions of 8 micrometer, and the interparticle spacing is somewhere at 0.5 micrometer. So that puts us here at an interaction parameter of 13. It's not quite there, but getting there. So with a very realistic projection, we should be able to go to 22, and there's even some headroom by employing now techniques that we have very recently. So we should have a really fair chance to go to this crystallization regime.
You have to be careful that this stays two-dimensional.
Yes, yeah, absolutely. We need very tight confinement because we need to be tight with respect to the dipole-dipole interaction energy.
How do you, again, that's also
optical.
Another.
For that, we borrow techniques known from optical lattices. You use interfering laser beams that can squeeze the cloud to an extremely flat system. I will show you like early, what we do there in a little bit more detail later. So what we care about, so this is all great. We can reach pretty strong interactions and all that, but how long do the molecules live? So we measure the lifetime of the molecular gas. So this is a log plot. It's a bit unintuitive to read. The long and short of it is that our molecular cloud at a fairly high density, nevertheless, only lives 10 milliseconds. That's not long enough to observe ground states there. So that's actually, when you calculate it, you will find that corresponds to unitary loss. Basically, whenever a pair of molecules collides, it will be lost with unit probability. And that's no different from any other system that have been studied to date. So basically, all molecular clouds were suffering so far unitary loss. It's the same thing here, and we need to do something about it. So that brings me to the last part. And that is our efforts to actually create a collisionally stable sodium cesium gas. And we try to answer the question, can we actually do this? For that, we need to dive ever deeper into the internal structure of the molecule. So far I told you we create the molecule in the low vibrational ground state, but we also create each molecule in our system in a very specific hyperfine state. Turns out sodium cesium has in the rotational ground state 32 hyperfine states, and we prepare the molecules in this particular. It's not the absolute hyperfine ground state, but it doesn't matter because there's very little coupling between these states. So we could create a spin polarized gas of molecules. So it's 32 states in the rotation ground state. Now, we want to implement a technique that relies on a coupling between the rotational ground state and the first rotationally excited state. In the first rotationally excited state, we have 36 states. But now comes to rescue something that initially we didn't like, but is now very helpful, is that we need to work at very high magnetic field, 864 Gauss. But that leads to a simplification of the level scheme for the rotationally excited state behind the Paschen-Bach regime. And basically, it simplifies the allowed transitions dramatically. So the number of allowed transitions dramatically, and we expect some very simple rotational spectra. So the next thing we built is also something very exotic in the field. We built a microwave system that can create microwaves of defined polarization. For this, we developed a 4 antenna array, and between these antennas, you can tune the phase, and that allows you to make sigma plus, pi, and sigma minus microwave polarization in a defined way. This has not been done before in any comparable setup. With that, then we can take polarization sensitive spectra of the rotationally excited state. So I don't want to go into detail, just see basically the only difference between these spectra is that the polarization changes between each, and you see the changes in the spectra. This allows us also to precisely determine the rotational constant for the first time in sodium cesium. And we can drive now coherent coupling between the rotational ground state and the first rotationally excited state with defined polarization. And the only thing I want to say here is we find here a coupling strength of 42 megahertz for a sigma minus and very similar for a sigma plus transition. So we can drive coherent Rabi oscillations between these two states with a coupling strength of 42 megahertz. That allows us to make superposition states of rotational states with pi over 2 pulses on the scale of 6 nanoseconds. You already see there the potential of molecules for quantum information. You can make coherent superposition states very quickly on timescales faster than in superconducting qubits, but you have coherence times here that are thousands of times longer than in superconducting qubits. It's very interesting. But here we again don't care really about this. Here we care about the shielding. So I need like 5 more minutes, I guess. So we shine into our molecular gas a microwave that is resonant on a sigma plus transitions between the rotational ground state and the first rotationally excited state. That generates then rotating dipoles. And it turns out that when you do this in the right way, that you get time average potentials, and if dipoles rotate sort of in parallel, they repel each other side by side. So that gives you repulsive shielding. But you may ask what happens if they are rotating in a plane. You should get a time averaged attractive interaction. And there was actually a groundbreaking insight by Thijs Karman and Jeremy Hudson a few years ago, who found that there is a self-alignment procedure that if molecules approach this way and should see a time averaged attractive potential, they will actually realign themselves and they will start rotating side by side in this way. And there is not really an intuitive picture of that, unfortunately. You basically need to solve the eigenstates of the fully coupled channel system of the molecule in the presence of microwaves. We basically trusted that this could work. We didn't trust like completely in empty space. There have been especially work in Emmanuel's Bloch group, Bloch's group on sodium potassium. This came out like in February this year, but actually started this project already before. But it was good to see that it can actually work. Turns out in our system we have even more favorable conditions. We get even stronger Arabi coupling, and we get pretty good polarization purity in our system. And basically the question was, how much shielding can we get? So in the case of Emmanuel's paper, they got a suppression of inelastic collisions in their system by a factor of 10. So what could we get in bosons? Bosons should be worse because there's no P-wave barrier. So we looked at it. We take lifetime curves of our system, initially without shielding. I told you before, we get 10 milliseconds of lifetime. Then we switched on shielding with some random parameters, more or less, and we already see the dashed line is the non-shielded case, and we already see a substantial enhancement of the lifetime. The long dashed line is actually a fundamental limit that is related to noise in the microwave generator that is used for the shielding. So this is something we cannot fundamentally improve. But we improved our coupling parameters of the dressing, and we find that we can push the lifetime of the molecules all the way into the fundamental limit. We see now molecular gases with lifetimes of half a second, and this is actually data from like 1.5 months ago. We have more recent data where we really see that we can push the one body lifetime of the system to the 5-second scale. This means molecular gases are now useful in a way that is very similar to ultra cold atomic gases. And that's the main message, basically. So we get here, in fact, a shielding factor of 100. So that's actually more than in previous work.
Sorry, I have a dumb question.
Yeah.
What function is that?
The
previous one looked like an Paolo.
So this is basically a combination of 1 and 2 body loss. So the exponential.
No, but as a function of time, the number of molecules decaying here, like it seems like almost like it's not decaying and then.
Yeah, but it's because it's a log. Yeah, that's done intuitive. Yeah. Since the changes are so dramatic, this is just the only way to plot it. Yeah. Okay, so one more thing. We have a long-lived molecular gas now. Natural question is, can we cool it further? It's not yet functionally generate. And that's like really preliminary, but it's very encouraging. So we started evaporative cooling in this sample of molecules. Basically, we hold the molecules in an optical trap, and then we lower the trap depths of the optical trap and see evaporation of the molecules. And then what we need to see is thermalization. It turns out due to dipole-dipole interactions, thermalization is tremendously quick. We see thermalization in 20 milliseconds, where in atomic experiments, you have like seconds thermalization time in equivalent scenario. And we see that when we start with a cloud of 350 nanokelvin, we can cool to 120 nanokelvin. And then we do another evaporation step, lower the trap depths further, and we get cooling to 50 nanokelvin. That's some of the coldest molecular clouds ever achieved. And the phase space density is somewhere at point. We don't know 100%, there's some subtleties, but it's going to be somewhere between 0.2 and 0.4. It's pretty close to a BC of molecules. We are hopeful that we actually can make it to a BC of molecules in this system. Okay, good. I will skip the next part. This is the second setup in our group where we where we are working towards strontium optical tweezer setups for Rydberg physics. So I didn't bash it before when I said dipolar molecules are very interesting. Rydberg physics is very interesting too, and we're working on this on optical tweezer arrays, but it's really really a completely different setup. But I want to summarize. So I showed you how we create dipolar sodium cesium molecules, and we are on the way, or we have a stable dipolar gas. We want to bring it into the proper quantum gas regime by condensing it. And there are a lot of exciting opportunities ahead. So one thing is evaporative cooling. I showed you sort of the start of this, and the prediction is that you can get very healthy ratio between elastic and inelastic collision. And we hope that that gets us into PC. There's still uncertainty. We'll only believe it, of course, after we make it. So then the question was raised before, how do we confine the system into a 2D plane? So right now we are having it in a 3D gas. We need to compress it into a 2D plane. So there is a technique known from ultra-cold atom setups of accordion lattice, where you have two interfering laser beams, and by changing the angle of interference, you can compress adiabatically the system from 3D to 2D. That's a technique that was pioneered by Jean Dalibard, who is an expert on 2D systems. And with that, we should actually be in a position to study this fixed diagram. Then we are combining the setup actually with a high resolution objective. So let's say we are able to create a crystal. We would really like to image it atom by atom. And by this, we think there is really opportunity to establish a new modality for quantum simulation using dipolar molecules with interesting long-range interactions to quantum simulate interesting systems. There is also the potential for interesting non-equilibrium dynamics, because we have this, almost instantaneous control over dipolar interactions. A side note is, when you saw this setup of the accordion lattice, you can immediately ask the question, why don't you populate 2 layers? Well, that should be possible. And then seeing like interactions between layers of these dipolar molecules could be interesting in rich system itself. Then obviously, confining the molecules into lattice systems in 2D will be interesting, because it would open up a pathway to study extended Hubbard models with single side and single spin resolution. So, there's a prospect of creating interesting Mott insulators that arise due to long range interactions, and studying quantum magnetism using the dipoles of the molecules as effective spins. So there's tons of proposals about that. And a sort of a side note is that sort of similar physics to this fractional Mott insulators have just very recently been observed in more array superlattices. So really, kind of emphasizing at the very end, like one more point is that, also thermodynamically, the system that we are creating is quite interesting. So initially, you can think of it as a gas of weakly interacting molecules. But then with this microwave techniques and the electric field control, we can abruptly change the interactions in the systems. So we can go from a situation where the range of interactions is like fairly short to abruptly to a situation where you have overlapping interaction ranges. And that should really give rise to interesting scenarios for quench dynamics, and potentially also very interesting thermodynamics. System. Okay, so with this, I want to conclude. So the NaCs work has been done by this group of people. So one person I really want to point out is Ian Stevenson, who, as a postdoc in the lab, drove forward this effort with amazing energy, and he's looking for a faculty position. And I think he's an amazing person in the lab. And then the different elements of the work have been done by Aidan Lamb, Niccolo Vigali, Claire Warner, and more younger generation of students, Siwei Chang and Wei Jin Yuan. And about the tweezer setup, I didn't talk. That's the second setup, and we can talk about it later if you're interested and want to do this. I want to thank you for your attention.
handled a lot of questions. More
Yeah.
questions for Sebastian?
Sorry for, thanks for your patience.
Thanks for the nice talk, Sebastian. So do I understand correctly that in terms of physics, your first goal is this superfluid to crystalline transition? Okay. And so what would
So basically, the first interesting thing will be the dipolar superfluid. Basically, there is some overlap between this physics and the magnetic atom work that has been done with dysprosium and erbium. So this will be interesting. Also, studying sort of the roton spectrum that you expect there, and that directly connects then to the crystalline phase, also crystalline phase. Yeah.
But you also have a plan about mod transitions.
Yes. Yes.
And
So, basically this.
So that's a separate experiment.
Same experiment. Yeah.
Same.
There will be a lot to do. Yeah. So we'll have to pick at some point. I think if we get to this point here, I think there will be many directions. But for now, we are planning with the same experiment because we have no second one. So this is actually a real image. So we have these accordion letters prepared. So basically, ready as soon as we have. I think this will happen after we actually approach BSC. We'll try to confine it into these 2D planes, and then sort of 2D physics is the next natural.
Perhaps another question is, given the optical access in your cell and so on, what are the observables you can actually measure? What kind of spectroscopy can you do?
Yeah. So there is basically something that can work in the 3D gas very well is measuring the excitation spectrum. For example, the roton spectrum in 2-photon spectroscopy, very similar to what has been done with atoms, can work here. Here there are additional options with microwave spectroscopy. So for atoms,
so
RF,
more like outcutting.
Yeah, exactly. So this works. So that's sort of in the 3D gas, but then we have prepared already in the test setup high resolution objective. So basically, this is something we want to bring on as soon as we understand the system well enough.
And the RF outcoupling works by coupling to different hyperfine states like in atoms, or different rotational. Yeah.
So basically, I think the role we will have to see. I mean, this is early stage basically, but I think microwave spectroscopy can fulfill a very similar role in molecules that fulfills radio frequency spectroscopy between hyperfine states in atoms. So in some sense, there's still a lot of open questions. This is basically we need to understand what are the good observables. It's a kind of a real question. It's a new quantum system. We can borrow some techniques from ultra-cold atoms, but some things are also new, different, perhaps harder. Some are harder, some are easier. Might be really new.
Can you do Bragg spectroscopy and get the structure factor?
Yeah, on principle that should work too. Yeah, I mean basically there you would think of using 2 lasers with a different K vector that are kind of in proximity to an electronically excited molecular state, and it should work similar to the atomic case. Yeah.
Are atom species a necessary condition to prepare the molecule? Because imagine the rotational grounds, low vibrational ground state still has a much higher energy than BC.
Yeah. So initially for the atoms that we use to create the Feshbach molecules, we don't necessarily need to have them in a condensate. Actually, for much of the data, we don't condense them. Because you get high molecule number when you don't condense, and then especially now with the new insight that this may still be a motivation to work with condensates initially, because the temperature and the phase space density of the initial atomic gases to some degree transfers onto the molecular gas. So you start colder with the molecules, but it turns out now, since it seems evaporative cooling of the molecules is working quite well, maybe even better than in the atomic case, we may actually start with more molecules at a hotter temperature and then evaporatively cool very efficiently in the rotational ground state. That may be the better route. And that's how it looks right now. And then the second question, yes, the temperature is not relevant with respect to the rotational excitation energy. Rotational excitation energy is like gigahertz, so the temperature doesn't matter, but it matters with respect to the hyperfine splittings, which are actually just a few hundred kilohertz. So we want to have a BEC to be in a pure spin polarized quantum state, right? So basically, really, the visual picture is each and every molecule is in exactly the same quantum state, and if you reach BEC, it will be even in exactly the same spatial wave function. Yeah?
I had a question about the phase diagram that
Yes.
you've been showing. If I think of this line on this side as a pressure, effectively, it looks exactly like phase diagram of a system of atoms with short range repulsion and long range attraction. So I'm a little, it's kind of, what kind of calculation is this that in which they are staying, everything is repulsive, but staying together simply because of confining potential gives a very similar phase diagram. What is this a thought expected phase diagram, or is this something somebody has calculated?
Yeah, no, there's been, I mean, I give like 2 papers here, but this has been studied from the superfluid regime, quantum Monte Carlo, Switzerland, Prokofiev.
This confining potential and pure repulsion.
Yes.
So probably not the confining potential, but you can apply a pressure.
Yeah, exactly.
So I don't think they did this with the confining potential.
So
Yeah,
actually, just bridge it down.
Yeah.
In the experiment that you are building, you will be able to engineer the trapping potential with DMDs or things like that.
Yes.
Or what's your first goal? To do it with a parabolic trap or to do it with a flat trap?
The first thing to try is a parabolic trap, but it will be very hard because basically you need to have a depth on the wall that holds against the dipole-dipole interaction, right? Otherwise, you can just spill over the potential barrier. So basically, you need to have a hard wall in addition to the harmonic trap. So the simplest system to create practically is a fairly shallow harmonic trap with hard walls. And then in a second stage, you can even it out with a DMD to make out of the shallow harmonic even a flat potential.
Okay.
But practically, that's the second step because it involves some more technology to be integrated.
But that's the first order. I'm sorry.
And it probably didn't answer.
Sorry, finish your, I was going to propose that we carry on with
I have a
discussion
meeting
over
with them
lunch, but
afterwards. I'll ask.
finish your, okay.
Well, I was going to say that just to comment on Chandra's, I mean, because these are bosons, the 2 phases are pretty kind of not controversial, right? Weakly interacting bosons will be superfluid and
Yes.
strongly. But I guess the question to my mind is that a first order transition in between?
So how
And
does
then in that case, do we not expect some, more complicated, because you have long range interactions
Yeah.
that will frustrate first order phase transition?
Yeah, so that's a good question. And
Maybe
then,
like Kibbleston type arguments, microemulsions.
this is discussed in this context. That's the only thing I can tell you that
That's more delicate.
that's microemulsion phase is something that has been discussed. Also, what has been proposed is, and that kind of intuitively it seems to make sense, right? That you have a super solid phase in between.
Right.
And how this will really look in practice, I guess we'll ask the experiment. I mean, from my point of view, I'm going to ask the experiment.
Right.